So in the last video, we learned that electrons have quantum numbers, and those quantum numbers describe things like what the energy of the electron is and where it lives. So how do we look at something like the periodic table and see the quantum numbers, right? And that's our major goal for this video here, okay? So the way that we do that is first we have to learn how we put electrons on atoms, how we determine the 4 quantum numbers for every electron on an atom, because then that'll actually help us elucidate why there's 2 metals on the left-hand side, 2 columns of metals on the left-hand side, why there's 6 rows to the right-hand side of the transition block on the periodic table, right? It's going to be really beneficial to have a periodic table in front of you as we go through this video. I'm going to be referencing things like that throughout. So please make sure that you have it on hand because it's going to be very important just to be able to make these connections between quantum numbers and what the periodic table looks like, right? There are essentially 4 rules that we use to put electrons on atoms, right? And that's where we start. And then eventually we mesh it to the idea of what the periodic table looks like in terms of structure, right? The first rule that we use is called stability, okay? And essentially what we have with stability is that the lower the energy, the better. In general, electrons like to be at low energies. Now, we know from the last video that only certain energies are allowed. But no matter what the electron is going to try to do is get to those lower energy situations, okay? In general, that means a lower n, okay? Because remember, n is the quantum number information associated with energy, right? If you look at the periodic table that I give you, there's this period label on the left-hand side, okay? And you'll see like 1, 2, 3, 4. So hydrogen's in the first period, lithium starts the second period, sodium starts the third period, potassium starts the fourth period, so on and so forth, right? That period is actually the N with one major exception, okay? So the D's lag one behind. So, I mean, we're going to go over this again, but just to kind of preview it, if you look at something like SC, so SC is element number 21, right? It's in period 4, but actually it has an N of 3, right? And we'll see that in general, you can just look at the period for the N, but then the D's lag one behind. Well, how do I even know that the D's are in that transition element sequence? Well, we'll get there, okay? But I just want this here to preview so that when we do get there, you have a little bit of forewarning about it, and then when you review this video, you remind yourself, oh yeah, the D's lag one behind in their N, right? The next rule that we have is Aufbau, which means build upon, right? And essentially, it's an idea that the electrons fit into slots, okay? So the first electron on an atom always has the same 4 quantum numbers. That's its home, that's its zip code, that's the slot it goes into, right? When I go to something like carbon, which has 6 total electrons because it has a Z of 6, okay? Well, carbon has its first electron fit into that first electron slot. The second electron slot is the same for all elements. The third electron slot is the same for all elements. That's what it means. Everything just kind of fits into the correct 4 quantum numbers based off the number of electrons that are on there, right? First electron has a set of quantum numbers for every single atom, right? It always has the same set, right? And you could say this about any electron. I just used the example of the first here, okay? The next idea is the Pauli principle, which is that no 2 electrons can have the same 4 quantum number, which kind of makes sense because if electrons fit into slots, okay, then there's only 1 electron per slot, okay? So no 2 electrons can have the same 4 quantum numbers, right? All right, that amounts to there's 2 electrons per orbital, right? 2 electrons per orbital. And remember what we did last time is each orbital, right? The shape was determined by L, but each orbital had a different m sub L, right? So essentially what this is telling us is each m sub L that we eventually work our way down to, right? It can fit into electrons, one with spin up and one with spin down, okay? And again, this is a bit of a preview. This picture won't make sense until we kind of get there in this video. But again, it'll be nice to have in your notes right now, okay? 1 electron is spin up, 1 electron is spin down in every orbital, which has a label of m sub L. Excuse me. The final rule is called Hund's rule of maximum multiplicity. But for us this semester, Hund's rule is fine enough, right? And what Hund's rule tells us is that for a set of orbitals, you put 1 electron in each before doubling up. So where this matters is when orbitals show up as a set. And so from the last video, there were two types of orbitals that we care about this semester that show up as a set. And these are p and d orbitals. So when we fill p and d orbitals, when we're trying to determine the 4 quantum numbers for p and d sets, right, you put 1 electron in each before you double up, okay? So now with all of this, what we're going to do is we're going to develop, right, use of these rules and then how it coincides with information on the periodic table. Okay, so let's take a look at our rules and let's try to come up with the 4 quantum numbers for, all right, the last electron in, all right, and then let's start with hydrogen. Okay, and so what we're going to do is we're going to use our quantum number rules to determine the 4 quantum numbers for the last electron in each one of these species. And you'll see why I'm saying the last electron in a bit, and I'm going to reinforce some important points as we go along here. Okay, so hydrogen, if you think about hydrogen and you look at the periodic table, it has a Z of 1. So that means hydrogen has 1 total electron, so the last electron is actually the first electron. Okay, so where is this electron going to want to go? Well, it's going to want to go into the lowest energy state, right? So the lowest energy state, what's the lowest value of n we could have from last video? So hopefully you've memorized by now that n, the lowest amount it could be, is 1, okay? So n equals 1, bistability is where that electron is going to go. Well, if n equals 1, what values of L are allowed? Well, from our rules last video, when n equals 1, there's only one L that's allowed, and it's an L equals 0. And there's no ambiguity, there's no guessing. When n equals 1, L can only be equal to 0. Okay? Well, when L equals 0, there's only one M sub L that's allowed. And that's equal to 0. Okay, so well, this is going pretty good so far, it's pretty easy. Well, now we have some choices for M sub S. And if you remember, M sub S could be two things, plus 1/2 or minus 1/2. When it's the first electron in an orbital, we'll use plus 1/2, okay? So now here's the picture that we have in our head, right? We have an n equals 1 orbital that has an S shape. There's one orbital because M sub L can only be equal to, right, 0. And now there's a spin up electron in that orbital. Okay. Let's go to helium now. Let's try to think about what the quantum numbers for the last electron in helium would be. Well, helium has 2 total electrons. Where does the first electron go? The first electron goes here, right? So hydrogen's last electron, right, is the first electron on every atom, okay? So helium's first electron goes here, right? Where does the second one go? Because that would be the last electron in helium. Where does the second one go? Well, is there still room in this M sub L equals 0 orbital for an electron? And the answer is yes, because we know from the Pauli principle that no 2 electrons can have the same 4 quantum numbers, but that means that for every M sub L, I can have a spin up electron and a spin down electron. So is there room in the n equals 1 orbital? Yep. N equals 1, L has to equal 0, M sub L has to equal 0, but now M sub S equals minus 1/2. Okay, great. So now we go on to sodium. Where does the first electron in sodium go? It goes here. Where does the second electron in sodium go? It goes here. Ooh, sorry, lithium. My bad. Sorry about that. That's true, though. The first electron in sodium goes here, and the second electron in sodium goes there, because the first electron on any atom goes here, okay? And the second electron on any atom goes here. For something like lithium, okay, which only has 3 total electrons, 3 total electrons, the first one goes here, the second one goes here. Now, where does the third one go? Well, if we look for the third electron in lithium, right, is there any more room in this n equals 1 level? And the answer is no, right? For this n equals 1 level, there was an s orbital, and we filled it. Are there any more shapes in that n equals 1? Well, no, there's no more L's that are allowed, okay? And so we're kind of done with n equals 1 at this point. And you'll notice what happened in the periodic table. We went down to row 2. We went down to period 2, right? And that's labeled on the left-hand side of your periodic table. So guess what? Now we start filling n equals 2. Now when n equals 2, we have a choice here, okay? Because if n equals 2, there's two possibilities. I'm just going to write them down here. And L equals 0 or L equals 1. And we know that from our last video. So what do we fill first? Well, it turns out that on the left-hand side of the periodic table, we're always filling the L equals 0s first, right, on the left-hand side. We always fill the S's first, right? Remember, L equals 0 translates to an S orbital. L equals 1 translates to a P orbital. So for a given n, we'll fill the S's first. So then with that simple rule, and with understanding the structure of the periodic table where the first two rows are filling S's, sorry, the first two columns are filling S's, the 1A and the 2A, okay? We're going to go from n equals 2, L equals 0, okay? We're going to start filling there. Well, if L equals 0, for sure, M sub L equals 0, there's no doubt about it. This is the first electron going in, so M sub S equals plus 1/2 by convention. So then go to beryllium, Be, which is 4 total electrons. The first electron goes here, second electron goes here, third electron goes here. Is there room in this orbital for another electron? Yeah. Each S orbital can hold 2 electrons. So n equals 2, L equals 0, M sub L equals 0, and M sub S equals minus 1/2 would be the set of quantum numbers for the 4th electron on any atom, and that would correspond to the last electron in beryllium. Now when we go to B, notice we're at a different part of the periodic table. Is there still room in this n equals 2 energy level? And yes, there is. What we found out was that with n equals 2, if we use our quantum number rules, L could be 0, but we're filled up with there. All right, we're filled up in that level. All right, n equals 2, L could be 0, or L could be 1. Right. So now we're filling P's. Remember, L equals 1 translates to a P. Right. Remember, P's show up as a set. And how do I know that? Because if I use my quantum number rules from last time, I know when L equals 1, M sub L could be -1, 0, or 1. Right. It shows up as a set. So there's 3 different orbitals because each M sub L is a different shape, a different orientation of that shape, right? And remember, there are 3 P shapes, right? They show up as a set of 3. Okay, so here's where Hund's rule comes into play because I'm going to start filling with the M sub L equals -1, right? This is the first electron in there, so the M sub S is going to be plus 1/2. When I go on to carbon now, right, you might say, well, based off our logic from before, there's still room in this -1 orbital, but, all right, are there multiple orbitals of that shape? Sure, there's 3. So what does Hund's rule tell us? We put 1 in each, all spin up before we double up. So we put 1 in here, so where are we going to go next for carbon's last electron? We're going to go here, right? So for carbon's last electron, right, we're going to write this as n equals 2, L equals 1, M sub L equals 0, and M sub S equal to plus 1/2. Right? Nitrogen's electron then, n equals 2, L equals 1. Do I have another orientation of this shape? Do I have another M sub L I haven't filled yet? And the answer is yes. We use Hund's rule. We put 1 in each before we double up. Right? That's the last electron in nitrogen. Those are the same 4 quantum numbers for the 7th electron in any, right, atom. Now when we go to oxygen, I'm just going to write it back up here. Now we say to ourselves, okay, did we put 1 in each M sub L? Yep. All spin up. Is there still room in each one of these levels? Yes, there's still room in each one of these orbitals, right, for an electron, right? We could have a -1/2, right, M sub S in each. Well, now we go back and we start to do that, okay? So for oxygen, we say, all right, n equals 2, there's still room here. L equals 1, yep. Let's go back to the M sub L equal to -1, and let's put a spin down electron inside it. Okay, and then the pattern repeats from there. We're almost done with the second row. So let's do F and NE together. And you just keep going down in your notebook, right? So for F and NE, hopefully you can maybe do this by yourself. Go ahead and try to write the 4 quantum numbers. Maybe pause the video for each of the last electron. Say for the last electron in each of these species. Okay. For F, it would be N equals 2, L equals 1. Is there still room? Yep. There's still room in the M sub L equals 0 to put a spin down electron. And then finally for neon, N equals 2, L equals 1, M sub L equals +1, and M sub S equals -1/2, because there's still room in that orbital set for the last electron it can fit in there. We hit the noble gas again, and look what happens when we go to sodium. Okay. When we go to sodium, we go to a new N. Okay. We're done with N equals 2 at this point, and now we do N equals 3, right? L equals 0, M sub L equals 0, because we fill our S's first, and then M sub S equals +1/2, because that's the first electron going in there. And the last one we'll do before we kind of switch up our viewpoint here is magnesium. Is there still room in that S for an electron? Yep, there's still room in that S for an electron. Do we have to worry about Hund's rule for S's? Nope, because there's only one possible M sub L. It's not like our p orbitals, right? It's not like our p orbitals. There's only one M sub L possible. So this is the first way we kind of show this, all right? And hopefully you're following the patterns. Everything's coming from our quantum number rules and the 4 rules that we talked about at the beginning of this video, okay, in terms of how the electrons are slotting in there. Now, the one drawback from this is we're looking at the last electron in each, and I was trying to make the point again and again and again, well, there's all those other electrons below it. The first electron is like hydrogen's last electron. The second electron on any atom is like helium's last electron, and so on and so forth. What we do is we draw these things called orbital diagrams that really help us see all of the electrons. And orbital diagrams also help us note a pattern that kind of emerges, okay? So we're going to draw a big orbital diagram to start with. Let's do something like P. All right, so let's just pick a random one. And here's how we represent an orbital diagram. It's all our quantum number information, but it's all in one picture. And what we'll do is we'll draw these lines, and that line is an orbital. So each one of our lines can fit 2 electrons in it, okay? Well, where does the first electron on any atom go? Well, the first electron on any atom goes into that N equals 1, all right, N equals 1, L equals 0 position, all right? So if you go back and look at your notes for hydrogen, all right, starts at N equals 1, L equals 0. We translate that L equals 0 to an S, okay? Now that has an M sub L of a 0. Now sometimes we don't write that in there because we know what the M sub L is for an S, all right? But just the way I'm going to do it this semester is I'm going to write the M sub L in there as well, all right? So this is N, this is my L translated to the appropriate letter, and I write my M sub L underneath there. So the 2 electrons that go in there, right, this would be like hydrogen's electron, and remember when we draw M sub S, we draw a half arrow up, so if we have a spin up electron, it's a half arrow up. And then helium, right, remember we said with helium, in this N equals 1, L equals 0, M sub L equals 0 space, is there room for another electron? And the answer is yes. So that would be like helium's electron. So notice, even for P, okay, the second electron always goes in the same spot, right? So where do we go for the third electron now? Well, for the third electron, which is lithium's electron, we go down to a new period. And so we're in the 2, right, N equals 2 energy level now. Well, when N equals 2, right, when N equals 2, we know we start filling the S's, even though you could have S's and P's. Remember, we filled N equals 2, L equals 0 first. Well, when L equals 0, M sub L can only equal 0. So then lithium's electron was here. But notice hydrogen's electron's there, helium's last electron is there. All the electrons are fitting into slots, so this is kind of easier to see the alpha at this point. What about beryllium? Is there a spot for another electron there? Yep. So the fourth electron on any atom goes there. Now we're done with n equals 2, L equals 0. But we do know, okay, that n equals 2, L equals 1, right, is possible as well. So now we're filling the two p's, right, two p's. Right? Now the two p's, there are multiple m sub l's that are possible. When we have a p, L equals 1, so m sub l could be -1, 0, or 1. So we write those in there. Oh, and now we can really see Hund's rule. So please follow along the periodic table here, because we're going to see a pattern emerges, right? So what about the fifth electron? What about boron's last electron? Well, we put it here in terms of the 4 numbers we picked. Then when we went on to carbon, we said, am I going to double up here? No, what Hund's rule says, for something like carbon's last electron, we would put it here, all right? We're going to put 1 in each before we double up. For nitrogen's electron, we're going to put it there, all right? And remember this right here. I'm going to actually change to a different color. This is nitrogen's electron configuration. This is nitrogen's orbital diagram, all right? Don't worry about electron configurations quite yet. This is nitrogen's orbital diagram right here. Let's go into oxygen. Oxygen is when we started doubling up, so we went back to the -1, right? Then for fluorine, here, right? And then for neon here, okay? Now we're dealing with P, right? So we got to keep going at this point. And so P has 5 more electrons to put on there. So we now go to sodium. And sodium, we're down into a new position. We're down into a new N level. So for sodium, we're going to start filling the 3 S's, right? Sodium, okay, magnesium. Now we go over, all right, and what do we fill next, all right? Well, when n equals 3, all right, L could be 0, L could be 1, or L could be 2, okay? So what we do is we fill the P's next. Now, how do I know I'm filling those P's next? Well, look at where we are in the periodic table, all right? Do you notice how the P block, which is on the right-hand side of the periodic table, where we started filling B, C, N, O, F, N, E? Notice there were 6 slots there, right? And there's 6 columns on that periodic side of the periodic table. There's 6 columns on that side of the periodic table, and there's 6 slots for electrons, right? When you have p orbitals. Now we get to like aluminum, silicon, phosphorus, sulfur, chlorine, argon, and we see there's another set of 6. But where are we filling? We're filling in the P's, right? Let's go back to the S's. On the left-hand side of the periodic table, whenever we hit an S, right, what do you see, right? Group 1A, Group 2A, there's 2 columns. Now why? Because those S's are associated with 2 slots, right? So when we look at hydrogen and helium's electron versus lithium, beryllium, versus sodium, magnesium, on the left-hand side of the periodic table, the far left-hand side of the periodic table, there's 2 columns because S's have 2 slots. So let's keep going with phosphorus, right? So we're at aluminum. Where's aluminum's electron going to go? It's going to go here. What about silicon? Well, we use Hund's rule, 1 in each before we double up, okay? And now finally we're at P. And where's it going to go? It's going to go right there. So for the last electron in P, right, this shows all of the electrons in P, but for the last electron in P, it has an N equals 3, L equals 1, M sub L equals 1, right, and M sub S equals +1/2. That is the set of electrons that it has for the last electron in phosphorus, which would be the 15th electron on any atom, okay? Now look at this structure right here. The S's are filled, and then you have 3 electrons all spin up in your P's, in your p orbitals. That's what phosphorus's diagram looks like at the end. Remember nitrogen? Nitrogen was an S that's filled, and then 1, 2, 3 up, okay? So if you look at where we switch colors here, we have 1 in each and then we're done. And here we have one in each, and then we're done. And notice that nitrogen and phosphorus, they're above each other in the periodic table. Sorry, they're in the same column, all right? Nitrogen is here, and P is here. This pattern repeats itself over and over again. Just like the point I made that we're filling in like these 6 electron columns on the right-hand side of the periodic table, this pattern keeps going, right? If you look at something like AS, right? If you look at AS, we can actually predict what this looks like, all right? Just with information that we already have. Because N had a certain structure, okay? And then P had a certain structure, okay? AS is going to have the same structure, right? And so what we can do is we can simplify our notation a bit, right? And you notice here how we switched to a new N after we got done, right, with the noble gas. These noble gas configurations, right? So this right here, what I've put underneath in a box here, this looks like neon, right? It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. It looks like how 10 electrons fit on an atom. That looks like neon, right? So sometimes we get lazy, and what we do is we say, okay, well, I don't want to always start at 1s because I realize the Aufbau principle exists and we're always going to fit in these slots as we go. When I look at something like P, let's just look at the new stuff past the noble gas. And so what we do is we use square brackets and show the noble gas. And then we go on from there to write 3s, right? 3p. Okay? These mean the same thing. All we did is we wrote this in shorthand saying, okay, yeah, everything slots into the same thing up until neon. The noble gas configurations are going to be important for us, so let's just call that square brackets neon and then write the new stuff from there, right? So let's do the same thing from AS, and then now we get to talk about how the D's lag one behind, right? But what we'll see is that the ending structure of AS, it looks like our nitrogen structure, right? And it looks like our P structure. And so that's where we can just kind of use the periodic table to see these patterns, right? And to be able to predict for any atom, right, what the orbital diagram would look like, right? So for AS, if you look at the noble gas that's before it, okay, if you look at where you would be filling, if we kept going and we fill here, what we would end up with is argon as a noble gas, okay? You always pick the noble gas before it because then what's the new stuff after the noble gas? Remember, that's how we frame this, right? Well, the new stuff after the noble gas, argon, right, for AS, right, starts with, all right, potassium. So we're in period 4 now. So remember what we do? We use that as our N. We're in the left-hand side of the periodic table. We're filling the first 2 columns. The first 2 columns are always S's, right? So potassium, right, and its orbital diagram would be this, okay? So hopefully you can see that. Hopefully you're picking up in these patterns by now, right? Calcium then, right, would go here. And now we're in the transition metal block. And if you count across and you see how many columns there are in the transition metal block, this will make perfect sense. There's 10. Now, why does that make sense? Because we're filling the D's. The first 2 columns on the periodic table, we fill the S's, and there's 2 slots. The middle part of the periodic table, we're filling the D's, and there's 10 slots. Why are we filling the D's and there's 10 slots? Well, if L equals 2, what M sub L's are allowed? -2, -1, 0, 1, and 2. There's 1, 2, 3, 4, 5 different M sub L's. So why are there 10 slots in that transition metal block? And why are we always filling the D's there, right? Because each one of these can hold 2 electrons. So a set shows up of 1, 2, 3, 4, 5 orbitals, right? And these are going to be d orbitals. Now here's where the N stuff gets a little bit tricky. Remember how we're filling the 4s here? And we can look at the period to determine N, right? The D's lag one behind. So what we're actually filling here are the 3 D's. But if you look here, then we can kind of understand, all right, based off our filling rules, how these would go on. Now, what actually happens in a transition metal block is that lots of weird stuff occur, and I'm never going to ask you about transition metal configurations, because just like early in the semester, they have different charges, they're just trouble to deal with. It'll be the same thing here with electron configurations, but if this was going to fill normally, okay, this would be SC's electron. Ooh, let's write the M sub L's in here. -2, -1, 0, 1, and 2, right? SC's electron, right? T, I, V, C, R, right? M, N, F, E, C, O, N, I, C, U, Z, N. We have 10 slots, all right? 10 slots. And so there's 2 electrons in each one of those orbitals. Now we're on the right-hand side of the periodic table, and we see there's 6 slots there. What are we filling on the right-hand side of the periodic table? Just like the other examples we're talked about, we're filling the P's, but we're not filling the 2 P's anymore. We're not filling the 4 P's anymore. Sorry, 3 P's anymore. We're filling the 4 P's, right? P's show up in a set of 3, -1, 0, and 1 as the M sub L's, okay? So now we're trying to get to AS, right? So this would be the last electron in GA. This would be the last electron in GE. And then this would be the last electron in AS, okay? They're all going to be spin up by Hund's rule, okay? But if you notice, nitrogen's configuration, right? Just going to kind of circle in blue here. Nitrogen's configuration, right, at the end here in the P block. P's configuration and AS's configuration of electrons, they all have the same pattern. And so then this repeats over and over and over again. So the structure of the periodic table is really about filling orbitals, right? There's 2 columns on the left, group 1A and 2A, because there's 2 spots for S electrons. There's a transition metal block that has 10 slots available, because there's 10 electrons you could fit into the D's. And the only thing you remember is that the D's lag one behind, all right? And then finally, all right, there's 6 slots on the right-hand side of the periodic table, because there's 6 spots, all right, for P electrons, okay? So a couple things to finish out this video, because there's a lot here to digest and a lot to practice, okay? There's one other representation I want to talk about, and that representation is called an electron configuration. An electron configuration has less information inside it, okay? But it's important to know how to do. So let's do an electron configuration of SN. Here's what we do. We could use the noble gas shortcut like I showed you in the last example, but just to start with, I just want to show you like a full example. Now, SN has 50 total electrons, okay? Where do the first electrons go? They go into the 1s. All right, now we're going to represent the number of electrons in that 1s situation with a superscript, okay? So we have to fill the 1s with 2 electrons to start off, all right? How many electrons there are on SN, all right? So the electron configuration is representing these guys as superscripts. Where do we go after the 1s? Then we go to the 2s, okay? And if you think about everything we did this video, all right, this follows the same pattern. How many electrons did we put into 2s? We put in 2 electrons. Then we went to the 2p. Now, how many electrons do we put in there? And we put in 6. And we can see how we're losing information now, all right? We don't see the M sub L information. We don't see how those electrons are arranged in different orbitals. All we're getting is just a big number of electrons, okay? Like the gross number of electrons. And that's fine. That's what electron configuration shows, all right? Then from there, we went to the 3s. And we filled it. Then we went to the 3p, and we filled it with our examples, okay? You're going to keep writing to the right here. I'm eventually going to run out to the room. After the p, though, what happened? Okay, so we were out, and we had to go down to a new period. So we went to the 4s's. Then what did we fill after that? We filled the 3d's. We remembered that the d's lag one behind, and we put 10 electrons there. After we filled the 3d's, where do we go? We go to the 4p's, and we're going to fill with 6 electrons, okay? Now, we're getting really close to, all right, where we should be for SN. So now we're at our 5th period, okay? So we're going to write 5s2. So after we write 5s2, where do we go next? Well, now we're in the transition metal block, so pick up the pattern. Now we're going to be filling the 4ds. And to get all the way over to Sn, all right, we're going to need to put 10 electrons in those d orbitals. Okay? Well, after those 10 electrons, now we're finally in the p block again. So we're going to be filling the 5p's. And how many electrons do we need to get over to Sn? We just need 2 more electrons. So this is an electron configuration, okay? And like I said, there's a lot of missing information here. We could use, all right, a noble gas shortcut with this. If we look at the preceding noble gas, it would be Kr. So we could use a Kr in square brackets, and then from there we could write 5s2, 4d10, 5p2. And this describes, all right, how those electrons are going on there in a little bit of detail. It tells you how many electrons there are, right, for a given set of orbitals. Okay. All right. So this is a pretty comprehensive example. We worked all the way down to the 5s, but then the pattern repeats itself. Don't worry about F's, and I'm not going to ask you questions that involve F orbitals this semester. All right. Don't worry about the F orbitals. You're essentially going to be, you know, responsible for anything above where the F's are. The F's are the lanthanides and actinides, and I even cut them off of your periodic table so you won't worry about those, okay? So what you want to be able to do after this video is be able to think about, you know, those 4 rules we talked about at the beginning. Think about the 4 quantum numbers of every electron on an atom, be able to write orbital diagrams and electron configurations. But everything intertwines. If you kind of get the rules associated with the quantum numbers that we talked about in the last video, then you'll see that those are the things that manifest on the periodic table as all this information that we can represent in different ways. Okay. So just as review, all right, I'll give you a review at the end of this slideshow instead of at the beginning of the next. Okay. Make sure you can look at your chapter 6, chapter 7 slideshow. Look at slide 8 and look at slide 9, right? And what you'll see about this is it looks like a periodic table, but quantum number information is being shown, all right? Now, you don't have to worry about the transition metal block. You have to know that there's 10 electrons that go there. So don't worry if you see some goofy things in there, but you should be able to pick up on patterns, okay? You should be able to look at the periodic table and see these patterns, and we discuss these patterns. It's a nice little review after this video to go look at these slides and say, okay, yeah, I kind of get it. And if not, as always, make sure you contact me with any help that you need, all right? From here, we're going to go on and get a couple more definitions down, and then we're going to actually try to say, okay, well, now that we understand how electrons go in atoms, what happens to these electrons to actually make bonds, and can we represent the structure of molecules that are being formed, okay? And that'll be, like I said, the final videos that we have this semester coming up.